Okay, so the second half of 1.2 is over symmetry. There are three different types of symmetry that a graph or function can have. The first one is symmetry with the x-axis. So the way you're going to test for symmetry with the x-axis is you're going to replace the y with a negative y and simplify it. So an example of a graph that would have symmetry with the x-axis could be a parabola that is on its side. Okay, because if you were to think about it, if we could fold that on the x-axis, the top and bottom would line up with each other. So that's the first type of symmetry. The second type of symmetry is symmetry with the y-axis. Okay, so an example of that, so this would be x-axis symmetry. Okay, so an example of that, y-axis symmetry, would just be a regular parabola. So again, if you could take that and fold it on the y-axis, the left and right should match up. And the third type of symmetry we don't really talk about often, and that is symmetry with the origin. So an example of a function that has symmetry with the origin is a cubic function. Okay, so when you're looking at it, the way you can determine if it has symmetry with the origin is that if you can rotate it 180 degrees and it matches up exactly the same, then you can tell that it has symmetry with the origin. So how do we test for this algebraically? Well, just think opposite. If we're trying to test for x-axis symmetry, we're going to replace the y. If we're trying to test for y-axis symmetry, we're going to replace the x. But if we want to test for the origin symmetry, we have to replace both. After we replace it, we're going to simplify it to see if we are back at the original equation that we started with. So let's go ahead and get started. So let's look at this first example. So I'm going to take these other ones off the screen for now. Okay, so let's look at this function. Y squared equals x plus 4. So let's start off by testing for x-axis symmetry. So again, I'm going to replace the y with a negative y. And then I'm going to simplify it. Well, negative y squared is equal to positive y squared. So if you look, notice we are back at the original. So the answer would be yes. This does have x-axis symmetry. Let's go ahead and check for y-axis symmetry. So when I'm checking for y-axis symmetry, we're going to replace the x with negative x. Well, negative x to the power of 1 is negative x. So what we're left with is not a match to what we began with. So the answer is no. This does not have y-axis symmetry. So, well, let's go ahead and check for the origin. And when we're checking for the origin, we have to replace both. Okay, so I'm going to put in a negative y and a negative x. And when we simplify, we have y squared equals negative x plus 4. So the answer is no. This function is not a function, sorry. This equation only has x-axis symmetry. Okay, so now let's look at question 2. So let's begin by checking for x-axis symmetry. So we're going to have a negative y in place of positive y. And when that simplifies, we are left with negative y equals x to the fourth minus 1. And that is not a match. So that is a no to the x-axis symmetry. So now let's look at y-axis symmetry. When I put a negative x in, negative x to the power of 4, anytime you take a negative 1 to an even index, it becomes positive. So we're actually left with y equals positive x to the fourth minus 1. Well, that is a match, so that is a yes. Yes to the y-axis. And lastly, let's check for origin. So we have negative y and negative x. And when we simplify it, we're left with negative y equals x to the fourth minus 1. So again, that is a no because it has to match. Okay, now let's look at example 3. So x-axis symmetry. So I'm going to put a negative y in. And that just simplifies down to negative y equals the fifth root of x. Well, that's not the same, so that's a no. Moving on to y-axis symmetry. And we put a negative x here. So when you take the fifth root of negative x, you're actually taking the fifth root of negative 1 and the fifth root of positive x. The fifth root of negative 1 is negative 1. Okay, because if you multiply negative 1 5 times, you actually do end with a negative 1. So that is equal to negative 1. So that negative is going to come out, but the x has to stay. That is not a match. Or we could just say negative fifth root of x. But either way, that's a no. Lastly, let's look for the origin. And we're going to replace both. So we have negative y equals the fifth root of negative x. And we already know what the fifth root of negative x is equal to because we have to check that for the y-axis symmetry. So that's just a negative fifth root of x. So looking at it, you may think, oh, this is not the same because both sides are negative. Actually, they are the same because we can easily divide both sides by negative 1. And we will be back where we started. So if there is a way for you to get back to the original, as long as you're doing that operation on both sides, it's legal. So the answer is yes. This does have origin symmetry. So I'm just going to kind of give you a quick sketch of that graph. It looks something like this. And if you were to rotate that 180 degrees, it would be a match, which is why it is a yes. 2 more examples. Let's look at number 4. Okay, so x-axis symmetry. So that would be negative y equals 3x cubed plus 2x. That is not a match. So our answer is no. This graph would not have x-axis symmetry. So now let's look for y-axis symmetry. So we have y equals 3. And now we have to substitute that negative x in two different places. So the negative x goes here and here. So what do we get? Well, negative 1 to the power of 3 is negative 1. So we have y equals negative 3x cubed minus 2x. And that is not a match. That is a no. So let's check to see if it has origin symmetry. And I wrote kind of big, so I'm going to squeeze that in over to the side here. So origin symmetry. We have to check both. So I have negative y, and that equals 3. And then I have a negative x here. And then I have a negative x here. So the good thing about checking for the origin is that it kind of brings the x-axis work and the y-axis work together. So it's a little faster to do this check. So I already know that this is negative y, and this is going to be negative x cubed, negative 3x cubed minus 2x. But again, I can easily divide. It may look like it's different, but I can easily divide everything by negative 1. And it is possible for me to get back to an exact match. Therefore, it is a yes. This has symmetry with the origin. One last question. And let's look at number 5. So to check for x-axis symmetry, I am going to replace the y with a negative y. And when we do that, we get x squared. Well, negative 1 squared is positive 1, so it's x squared plus y squared equals 16. So the answer is yes. So now let's check for the y-axis symmetry. Replacing the negative x. Again, negative 1 squared is positive 1. So we get another yes. Well, let's see if it's a 3 for 3. Let's check for the origin. And we have to replace both. And what happens? Well, they both become positive. So this equation has symmetry with the x-axis, the y-axis, and the origin. And I don't know if you recognize what this equation represents, but this is actually a circle. And if you think about it, it makes sense. This circle has a center at the origin, and the radius is 4. So if you were to draw this circle, you could see that the graph of a circle, if you fold it on the y-axis, both halves will match up. If you fold it on the x-axis, both halves will match up. And if you take the circle and rotate it 180 degrees, it is still going to be a circle. That concludes the end of Unit 1.